In this video, we're continuing our section on partial fractions, and we'll look at the third case, which is, what if my denominator, q of x, has a quadratic factor that does not factor further? So let's look at an example. Let's suppose that I'm trying to find the partial fraction decomposition of this fraction. On the denominator, we have this quadratic factor. This thing has degree 2. And this linear factor, which has degree 1. There's a couple ways I can tell that this quadratic does not factor further. One of them is to use the quadratic formula. So using the quadratic formula, there are x equals negative b plus or minus square root, that whole thing. The roots of this quadratic are, it turns out we'll get negative 1 plus or minus the square root of negative 11. And then all over 6. But because we have this square root of this negative number, that is not a real number. And that means that this quadratic doesn't factor further unless you allow imaginary numbers, unless you allow complex numbers. But in our class, we're not going to use those at all. We're just going to focus on reals. So for our purposes, this quadratic does not factor further because it doesn't have real roots. So what does the partial fraction decomposition look like for something like that? Well, first off, I can split up my fraction into, in this case, 2 fractions added together. This first quadratic factor becomes the denominator of one term, and this linear factor becomes the denominator of a second term. For the numerator, what we do is we take the degree of what's on the bottom. So for this thing, it's degree 2. And on the numerator, it's something of degree, you subtract by 1. So it's going to be degree 1. So a degree 1 polynomial looks like ax plus b. So it's not just a constant term, it's a degree 1 polynomial because it's degree 1, whatever the 1 less than the degree of the denominator. For the next term, we've seen things like this before. The numerator is just a constant, which I'll call c. I can also apply this whole subtract 1 from the degree idea to it because the denominator has degree 1. And if you subtract 1 from that, it's degree 0. But degree 0 is just a constant polynomial like this. All right, so I got the setup. Now I need to do some algebra so I can solve for these coefficients. So let's clear the denominators by multiplying both sides by everything in the denominator. 3x squared plus x plus 1. And then also by x minus 4. If I do it on the left, I have to multiply the whole thing on the right by that as well. So 3x squared plus x plus 1 times x minus 4. So on the left, it'll cancel out the denominator entirely, and I'll get 9. On the right, we got to take this whole thing I'm multiplying by, multiply it by this first fraction, and multiply it by the second fraction. For the first fraction, it'll get rid of the 3x squared plus x plus 1, and we'll have ax plus b times x minus 4. For the second fraction, it'll cancel x minus 4, and we'll have plus c times 3x squared plus x plus 1. All right, and as we've seen before, once I've cleared out the denominators, now we plug in some nice x values so that I can solve for the coefficients. So I like to plug in x values that might make some of these factors become 0 if possible. So I know that if we plug in 4, that'll happen with this x minus 4 term. So if we do plug in 4, we get 9 equals, and then this part becomes 0. And then we'll get c times 48 plus 4 plus 1. Isolating for c, we'll get c equals 9 over 53. Okay, I'm just going to highlight that in orange. I will highlight that. Okay. There's no other numbers or like x values I can plug in that are quite that nice, that are going to make, things just become 0 like this. So for those remaining ones, let's try plugging in some small terms. So let's try plugging in x equals 0. If I plug in 0, I'll get 9 equals. This ax plus b just becomes b. So at least it makes the ax part go away. And then times x minus 4, 0 minus 4 is negative 4. And then I get plus c times 1. Okay, but I know what c is, so let's plug in for that. So I get 9 equals negative 4b plus 9 over 53. If you rearrange for this and isolate b, it turns that b will be negative 117 over 53. It turns out if you do some more algebra, you'll end up getting that for b. So that is b. All right, we still got to solve for a, so I'm going to have to plug in some other small value for x. Maybe let's try plugging in x equals 1. So if I plug in 1, I get 9 equals, let's see, a times 1 is just a. And then we'll get plus b, but I know what b is, so let's plug in for it. Minus 117 over 53 times x minus 4. So 1 minus 4 would be negative 3. And then plus c. C is 9 over 53. And then the stuff in the parentheses, I got to plug in 1 for that. So that'll give me 3 plus 1 plus 1. Okay. Simplifying this, we got 9 equals, I can distribute the negative 3 to each of these terms. So I'll get negative 3a plus 351 over 53. So we're getting some big fractions here. And then I'll get 45 over 53 because this 3 plus 1 is 5. Multiplying 9 gives me 45. All right, if I rearrange this, I'll get 3a on the left. And if I move the 9 over to the right and I get some common denominators, it turns out we'll get negative 81 over 53. And then finally, if I divide the 3, I'll put an arrow here. We'll get a equals negative 27 over 53. So let me highlight that as well. Okay, so I got the a, I got the b, I got the c. We are ready to take those and write our partial fraction decomposition. Okay, so we are going to get our original fraction equals a fraction, two fractions added up, sorry, where the first denominator is 3x squared plus x plus 1, and the second fraction's denominator is x minus 4. So on the numerator of the first fraction, we need to put what a we highlighted in green, x plus b, and b was in blue. So ax plus b, I'll get negative 27 over 53x plus b, so that'll be minus 117 over 53. So ax, just want to highlight this. This is the b, this was the a, and the next fraction, we put c on the numerator, which is the 9 over 53. 9 over 53. For this problem, it just wanted the partial fraction decomposition, which means it just wanted up until here. It didn't actually ask me to do the antiderivative, thankfully, because if we did need to do the antiderivative of this, for this first term, it turns out we would have to complete the square on the denominator. We'd need a u substitution. And then eventually, we would pop out an inverse tangent. Okay, so there's just a lot involved in this antiderivative. And I mostly wanted to focus on, well, what does the partial fraction decomposition end up looking like if you have a quadratic term like this that does not factor? Okay, and there we have it.